For this lesson, we'll be focusing on analog to digital analog converters. Now, just to give you a heads up, we're going to be focusing on the digital signal processing side versus the power side. So we're going to be dealing with the analog digital converters as far as taking a analog waveform and digitalizing it and vice versa. We're not going to be doing the power side, which is like full bridge rectifiers. So let's just go over the basics. Analog to digital converters is the process of information in an analog form and is converted to a digital form. This is known as digitizing. And digital analog converters is the process of converting a sequence of digital code to an analog form. All right, so we're going to go over a few analog to digital converters and a few digital analog converters. Now, they're not going to be every single one, they're just going to be a couple of the common ones. The first one we're going to look at is known as the flash analog to digital converter. This uses comparators that compare the reference voltage with an analog input, which is inputted into an encoder to determine the output digital binary string. So in that sense, you're going to have several op amps going into an encoder, which based on where the waveform is at that point, will give an actual digital output or a digital string. The second analog to digital converter is known as the dual slope. Now this one's a little more confusing and complex. However, it's actually very common and when used in digital voltmeters. The dual slope analog digital converter uses a ramp generator or an integrated circuit to produce a slope characteristic. This slope rises and falls at a set time, then returns to zero. When that happens, the comparator latches low, the clock disables, which latches the binary count. So in a sense, it's counting how many steps this integrator ramps up, logs it, and latches it, and that'll be your output, and then it resets, and it continues doing this. So it basically keeps sloping up and then resetting. The last analog to digital converter we'll be looking at is the Successive-Approximation analog to digital converter. Now this one's kind of exotic, but at the same time it's actually very simple, and it's actually widely used in a wide spread of applications. In a sense, it's a simplified trial and error circuit. This converter uses a digital analog converter, which is odd, and then it uses a register and a comparator. And what it does is it actually compares the output from the digital analog converter with the analog input. And then it changes the bits in the register based on where that input is. So all it's doing is doing a trial and error and changing bits based on the analog input. Now we're going to jump right into digital analog converters. And the first one we'll look at is the binary weighted input digital analog converter. I notice most of these have very long-winded names. Anyway, this one uses a summoning amplifier that represents its binary input. So in a sense, you're using an inverting amplifier and you're adding inputs to it, and the gain will affect your actual analog output. So every time you want to add a bit to this summoning amplifier, you're going to have to add another resistor in line to your input, and you have to double that resistance. That's where the disadvantages come in, because there's two disadvantages. The first one is it's difficult to maintain resistor tolerance for all those resistors. Every time you add a different resistor, it has to have very specific tolerance, and that's very difficult to achieve. Also, when you do that, it's also difficult to mass produce all these amplifiers or all these converters consistently. The last converter we'll look at is known as the R/2R ladder. Now this one is similar to the binary weighted input digital analog converter, except it can overcome those resistance tolerance issues by only using two different resistor values. So you're still using an op amp, however, you're actually using two different resistor values, just R and then 2 times R. And you're still doing an inverting amplifier, you're just manipulating it in a different way. Now that we went over common converters, now we can start going over the performance characteristics. The first one we'll go over is the resolution. The resolution is the reciprocal of the number of discrete steps in the output. Basically, your resolution impacts the accuracy of your digital waveform. So think as a resolution when you're looking at the clarity of your television. The higher the resolution, the more clear or accurate your picture, your output is. Same thing here. And we also provide an equation associated with resolution. It would be your max voltage divided by the number of bits used. So the higher the number of bits, the better. This also coincides with accuracy. Accuracy is the comparison with the actual output with the expected output. So all you're doing is comparing the expected with what you get. And that's where quantization error comes in. And again, we have a video with this one that talks about these different resolution accuracies. Quantization error is the difference between the analog signal and the digital output. It's basically due to a rounding error. Now, if you want practice in this, you can look at our quantization video, or a pulse modulation video, and we go over this a little bit more in detail in that particular lesson plan. The next performance characteristic is linearity. Linearity is little to no deviation with your ideal straight line output of your digital analog converter. So when your bits increase on your input, you should see nice little steps, uniform steps on your output. When this doesn't happen, it's called nonlinearity. Next is monotonicity. It is the process of your digital analog converter increasing its output as increase in binary code. Now this is similar to linearity with slight differences. As the binary bit increases, you expect to see nice steps. Well, however, sometimes you can have non-monotoxic in which your output actually can decrease. If you look at the graph at the bottom right, it's supposed to be ideal. It's supposed to go up like nice steps. However, every now and then it will go in the reverse direction, and that's non-monotoxic. That's not what you do not want. That's the worst case scenario. The last characteristic is settling time. It's the time it takes for a digital analog converter to settle within plus or minus 1/2 the least significant bit of the final value. Now this is very similar to the op-amp settling time. So if you want the official definition or how to calculate that, just use the op-amp settling time. All right, let's go and do some example problems. All right, for our first example here, we want to determine the binary output code at 8 seconds of a 3-bit flash analog digital converter for the following analog signal. All right, so this nice little waveform here, that's going to be our analog input. And we want to determine our digital output based on this analog signal. All right, so the first thing we need to establish is, what is our resolution? In other words, for every volt, which bit is that? How many volts are in a bit? So I'm going to use this equation down here and start determining what our resolution is. So Q equals max voltage, which in this case is going to be 0 to 16 volts, that's 16 volts, divided by 2 to the n. Well, as I said, 3 bits, so our n is 3, and in this case 16 divided by 8, 2 to the 3 is 8, and I don't think we need a calculator for this. So 16 volts divided by 8 equals 2 volts per bit. So every time you have a bit increment, it's basically 2 volts. So in other words, when you go from 000 to 001, that's basically going from 0 volts to 2 volts. So which means every 2 volts, it's going to be an additional level. So I'm going to go ahead and put lines here because I want to eventually put a binary code right next to it. And then at the very top. So let me clean this up and I'll add our binary codes. All right, so for this level, 0, 0 to 0. As soon as you get to 2 volts, you have 0, 0, 1. Of course, you add 2 more volts. It's going to be the next increment up. And the binary number for 3, binary number for 4, 5, 6, and then 7. So right now we have 8 levels. 1, 2, 3, 4, 5, 6, 7, 8. Way to confirm that, L is your levels, 2 to the n, so that's going to be levels equals 8. So that confirms that. Now we want to determine what our output code is going to be at 8 seconds. So if you're actually going to look at this every second of the way, you can actually start writing a binary string for each second. For example, at time 1 second right here, and you want to turn that binary number, you move up till you see where it intersects the 1, and it looks like it's a little bit above the 2. We'll say 2.2 or 2.5. So right there, I'm going to assume it's going to be a binary string start of 0, 0, 1. And then if I went to the 2-second increment, it would be, looks like it passes a little bit right before 5. So I'm going to say that one is going to be 0, 1, 0. So you can see where the analog input is and to determine your binary string. Now I want to do 8 seconds, so I'm going to jump right to it. 1, 2, 3, 4, 5, 6, 7, 8. So at this point right here, how do I know its binary output? Well, following it up, it looks like it intersects right there, right at 101. So your binary output is going to be 101, because right now it fell right at the 10 mark, which if you divide it by 2, it's going to be your binary number for 5, which means your binary string is going to be 101. That one was pretty simple to get our feet wet with. Let's do another one. All right, for our next example, we want to turn the output voltage of the following binary weighted input digital analog converter with a binary input of 1101. Assume that the binary input is 5 volts TTL, and this is for a high input, of course. So this one's the opposite. Instead of doing an analog digital converter, we're going to be doing a digital analog converter. So this one, we have a binary input of 1101. And of course, that's going to be the most significant bit. So I'll go ahead and put it to the side here. So it's going to be 1101. And we want to determine the output. Now this one's pretty simple. To the right here, we have the equation for the binary weighted input for digital analog converters. Now this one's pretty simple. This one's mostly plug and chug, but you just got to pay attention how to plug and chug. So let's go ahead and determine the output. So V out, I'll put it down here, V out equals, it's going to be a reference voltage. Now I said 5 volts TTL, so we're going to say automatically it's going to be negative 5 volts because it starts with a negative right there. All right, then we're going to do parentheses. And then it says our feedback resistor divided by R. So in this case, it's going to be, that's our feedback resistor right here. So it's going to be 5 kilo ohms divided by, and it's going to be this resistor right here because we're starting with the most significant bit, D3. You always start with your most significant bit when you're doing these formulas right here because it can continue on forever. All right, so feedback resistor divided by R, that's this guy. It's going to be 5 kilo ohms. And this is going to be multiplied times your digital input. For example, D3. Well, D3, which is the most significant bit, has a 1 there. So that's going to be times 1. And then we're going to continue on. So it's going to be 5 kilo ohms, our feedback resistor, divided by, and that's 2 times R. So in this case, that right there is going to be 2 times R. It's going to be 10 kilo ohms. And then, is there a 1 or a 0 there? There's a 1. Okay. Moving on. Feedback resistor divided by, and that's 20K. And again, is there a 1 or a 0 there? It's a 0. So that one's going to be easy when doing the math. And last one, your feedback resistor. Forgive my handwriting as usual. 40 kilo ohms. Well, I'll throw units on all of them. That way it's consistent. All right. And is there a 1 or a 0 there? There is a 1. Okay. And then we'll close parentheses. So we got somewhat of a big equation here, but it's not that bad. Let's go ahead and start simplifying this down. So I'm going to say V out equals negative 5 volts. And I'm going to say parentheses. 5K over 5K is 1. And this is times 1. So this one's going to be 1 plus. Then we have 5K over 10K. That's pretty easy. That's 0.5. And it's going to be times 1. So 0.5 times 1 is 0.5. 5K over 20K is 0.25. However, it's times 0. So that right there is going to be a 0. And then one last time. And then we have 5K over 40K. And that's going to give us a sum of 0.125. And of course, times 1 makes it a 0.125 versus a 0. And we'll go ahead and close parentheses. I'll tell you what, I want to see if I can fit this down here. So your output voltage equals negative 5 volts, parentheses. And I'll just go ahead and add all this together. All right, and that's going to give us a grand total of 1.625. And if we multiply negative 5 volts to our sum there, it's going to give us an answer of negative 8.125 volts. So when creating a digitalized output, when you have that binary input, it's going to give you an output of negative 8.125 volts. All right, so that one was pretty easy to get your feet wet with, but I just want to go over how to do this equation. That way when you come across it, it's pretty easy as far as plug and chugging. All right, let's do one more example. All right, for our last example, we have a very unique one. A tank level transmitter is installed in a fuel tank to communicate fuel capacity. The transmitter uses reed switches, which are these guys right here, and it's sealed within a pipe, which has a floating magnet, which is usually a cylinder magnet, and it travels along this pipe to actuate these switches. Now, in reality, these switches are very thin, so when a magnet gets close to them, they actually touch each other and close, creating a current flow path. And as the magnet goes up and down the pipe, it actually closes these particular switches and then opens as the magnet leaves them. Pretty simple, and this is very common. These give the indication of liquid height within a given tank. So again, as the floater goes up and down, it'll tell you where the actual tank level or the liquid is inside the tank, and based on which switch is closed. All right, so based on the following circuit diagram of the tank level transmitter, determine the output signal for all reed switch levels. So this schematic right here is very common among some of these transmitters, and usually in the marine industry. So each switch determines what the liquid level is inside the tank. So switch 1 is where the floater would be at the very top, and as the liquid lowers, the floater is going to lower with it, which means switch 2 is going to be actuated and switch 1 will open, and then so on and so on. So if you're going to create a digital input for this, it's going to look something like this. So for switch 1, it's going to be 1 if the magnet was right there, and then 0, 0, 0. So 0, 0, 0. Same thing for the next one. When the floater goes down to the next level, it's going to be 0, 1, 0, 0. The float magnet lift off the switch 1, so that opened, and it closed switch 2, and then so on and so on. So it's going to continue on until it has all levels. Let's see if I can make this fit. So just by looking at this in binary form, this is equivalent to a base 10 number of 8, 4, 2, and then 1. So what's this translate to on the output of your op amp here? That's what we want to determine. So let's look at reed switch number 1. So this guy right here. Let's imagine this is closed and the other 3 are open. So we want to imagine this guy right here. So let's use this equation right here to determine what our output's going to be. Now keep in mind, if you remember the PowerPoints, right here is your most significant bit, and this is going to be your least significant bit. So we're going to start top and work our way down. So V out equals our reference voltage, which is going to be 12 volts. So it's going to be a negative 12 volts times, this is going to be your feedback resistance, which is 2 times R. Now they didn't give us a value for resistance, so we're just going to have and plug and chug what we see here. All right, divided by R, in this case, is just going to be R. It's going to be multiplied times D3, which in this case is going to be D3 since our most significant bit, because it starts with your most significant bit and then goes least significant. So this can continue on forever if you want it to. So for this one, we have D3, our most significant bit, which is going to be on. So it's going to be a 1, because it has a binary input of 1, divided by 2. And it's going to be plus. Now the good news is D2, or next significant bit, and so on, are both all going to be zeros. So which means it's going to be 0 over 4, 0, 8, 0 over 16. So which means there's no point in putting those in, but the rest of them are going to be zeros. So let's go ahead and simplify this down a little bit more. So V out equals negative 12 volts times 2 times R over R, and that's going to be multiplied times 1 over half. Well, multiplying that in there, it's going to basically turn that into 2 times R, and this goes away. So which means if you're doing simple algebra, these two cancel out, which means your first V out for this guy right here is going to be negative 12 volts, because V out equals negative 12 volts. All right, let's do the next level. Let's go ahead and say the float lowers a little bit because the tank's emptying a little bit and goes to the next reed switch, so switch number 2. So let's determine that one. So let me clean this up. So I'm going to do the same thing. We'll say V out equals negative 12 volts, 2 times R over R. Now for this one, this is going to be 0 over 2, so I'm not even going to put no point in putting zeros across the board again. So it's going to be D2, which is 1. This guy right here is 1, divided by 4. So multiply that together is going to be V out equals negative 12 volts times 2R over, and this is going to be 4R, which means 4R. You can cancel your R's out and do a little simplification. Say 2/4 is 1/2. So in that case, V out equals negative 12 volts times 1/2. And we don't need a calculator for that one. 1/2 of negative 12 is negative 6 volts. So our next one is negative 6 volts. All right, let's do the next one. Same song, different verse. V out equals negative 12 volts, 2R over R. And for our next significant bit, we have 1 over 8. And that's going to translate to negative 12 volts times 2 times R divided by 8R. And again, we're going to simplify this down a little bit more. The R's cancel out, and you're going to have negative 12 volts times 1 divided by 4, because I'm simplifying down 2 divided by 8 is 1/4. And of course, that's going to give me an answer of negative 3 volts. So that's going to be our next one, negative 3 volts. Of course, let's do the last one real quick. It's going to be V out equals negative 12 volts. And then our feedback is going to be 2 times R divided by R. And then our least significant bit is 1 over 16. So 1 over 16. And simplifying it down just like we did a couple other times. Negative 12 volts times 2 times R over 16R. Well, of course, R's cancel out. And 2 divided by 16 is 1/8. So V out equals negative 12 times 1 divided by 8. And that's going to give us a final answer of negative 1.5 volts. So I'll see if I can fit that in negative 1.5 volts. So we determined our actual output for each one of these reed switches. So let's see how it's going to look on an output graph. Let me clean this up. All right. So we have a little graph here so we can see how it looks. So looking at this, if this was going to be your output waveform, it's going to look something like this. So the first bit, which is when your tank is at its highest level, is going to be negative 12 volts, which means that's 15, 14, 13, 12 is right here. So that's negative 12. So at switch 1, and we're going to go all the way across till we hit switch 2, it's going to be negative 12 volts. And then at switch 2, when the tank actually gets to a lower level and goes to the next reed switch, it's going to be negative 6. It's going to drop, and that's negative 6 right there. So we're going to drop all the way till we hit negative 6. And then continue on until we hit the next reed switch, which is going to get us negative 3. It's 4, 3. And then lastly, when you hit the last switch, in other words, when it's close to the bottom of the tank, you're going to hit negative 1.5 volts, which, looking at this, let's see, it's going to be something like right there. So it has a very steep step, and then it gets a little bit lighter, but it's not very uniform, which means if you actually connect this straight to an analog indicator or analog meter, it's going to be very inaccurate and very crude of how you're reading it. However, if you put this through a signal processing unit and actually have it so when each one of these registers shift to the right, you can have it take the average and to determine where the tank level is. So let's just get our feet wet with different types of converters and how to use them and how to manipulate the equations. So if you have any questions, feel free to let me know, and I hope you all have a good day.